SwayamPrabha. Digital India. Educated India.
Okay, so far we have been looking at, we have set up the basic problem in tomography. We have discussed what the differences are, where tomography comes from, and what basic ideas underlie single projections, multiple projections, when you need multiple projections and so on. And we also discussed this idea of a Fourier transform, which as we will see today will be central in determining the actual cross section and inverting the actual measurements to get cross section information. So, I think we have a good background to get started with the actual formulation, where we are looking at how to reconstruct a cross section from a set of projections. Okay. So, that is the basic problem like we set up. We will do this for a 2-dimensional case first, and then I will touch briefly on the 3-dimensional case towards the end. It is a little bit more complicated algebraically, but the idea is more or less the same. So, let us get back to our discussion on Fourier transforms. So, I will just make a couple of notes. First, I discussed that the 2D Fourier transform was basically something that looked like this. If you have a function small f of x y, then you take this double integral and you will get its Fourier representation capital F of u v, like u is like a x direction frequency, v is like a y direction frequency. And we saw at the end that this particular form with an I here, sorry, this particular form is sort of representative of a line in 2 dimensions, and this is the equation of a line. Of course, depending on the constant you get families of parallel lines. So, whenever u bar dot r bar is constant or a constant plus some 2 n pi, you will get the same phase, right, because e to the power of 2 I pi is equal to 1. And so, you will get a family of parallel lines, and the direction of the line is basically tan inverse of the components of this, which is this. Of course, this was the vector u, and the direction of these lines is tan inverse of v by u. Okay. So, I will make a couple of changes to this notation. So, this notation is intuitive, this u dot r equals constant is intuitive, but it turns out if you instead use slightly different definition of the frequency, which has an explicit factor of 2 pi outside. So, from now on we will start using something like this instead of just u dot r, and the reason being that if you do not do this, then there will be factors of 2 pi that keep coming out, and we do not want to keep track of any factors of 2 pi. Okay. So, we will just put the 2 pi inside, and u will now be not like an angular frequency, but it will be like an actual physical frequency or a physical inverse of wavelength, right, not a wave number, but an inverse of wavelength, that type of thing. So, that is one piece of information. Now, towards the end I mentioned that there seems to be some relation between this family of parallel lines that we have corresponding to this tan inverse v by u for a given pair of values u comma v, or for a given vector u, and this is not a coincidence, right. So, if you think about the equation of a line, this is what the equation of a line in 2D looks like. N is a normal vector, normal to the line, and r is the position vector, and depending on the constant, this gives you the equation of a line. Okay. The constant of course determines how far from the origin the line actually is. If the constant is equal to 0, the line is passing through the origin. If the constant is positive, it is passing through the top right quadrant, and so on. Okay. So, this is just a slightly different way of looking at the equation of a line. Of course, you know that ax plus by equal to c, or y is equal to mx plus c, or whatever, this is the standard equation. This is the same as this, right. So, because r bar is x comma v, x comma y, sorry. Okay. So, with this in mind, the second notation I also wanted to mention is, you remember the Beer-Lambert law, we are going back to that now. So, this had if is I0 exponential of minus integral mu of xy along some line with some limits, does not matter for now. We will not look at if, but we will instead look at minus log of if by I naught. Okay. So, we will not actually look directly at the intensity that we measure, but instead we will look at the logarithm of the ratio of the measured intensity to the incident intensity. The reason being that this is simply this integral, right, and it is easier to work with this integral than an exponential of the integral. Okay, just a notation. So, this is what we are interested in. Since we know if and we know I naught, we know log of if by I naught. So, we have the value of this integral along various lines, and our aim of course is to try and recover the value of mu as a function of x and y, right. That is the problem we set up initially. So, we will now start doing some algebra for this with these two notations in mind. So, we will talk about what is called a line integral and excuse me, what is called the Radon transform. So, let us say this is our cross section. So, this is, let us say we have a square and inside the square this is our actual object. We are talking only about 2D for now, 3D case will come later. So, this is our bounds and the actual object is here. There is some variation in f or mu and mu of xy is non-zero inside this shape and it is 0 everywhere else, right. So, we want to be able to reconstruct this shape from a series of projections. So, I will leave out this bounding area because it is all 0 there. So, this is our field mu of xy. We will actually refer to it as f of xy, okay, just so that we can relate back to the Fourier transform. Good. Okay. So, when you take a projection, let us now draw some axis for concreteness. So, this is our x axis and this is our y axis, and when you take a projection, so let us say my light ray is coming like this, my x-ray is also light, it is coming like this. So, the source is here and there is a detector here, and at each point on the detector there is some type of charge coupled device that is sensitive to x-rays, let us say, and it picks up an intensity, right. So, let us take one of these lines. So, if you were to draw just one of these, we will just take this fellow. The normal to this line goes in this direction, right. This is the normal vector, normal to any of these lines, they are all parallel. So, normal to all of them is the same, but this is the normal direction, okay, or this it can be up or down, does not matter, right, whichever normal. So, let us now take assume that this normal makes an angle theta with the x axis, okay. So, for normal I will probably use the same color again. So, this normal line makes an angle theta with the x axis, okay. So, the n hat is basically cos theta comma sin theta, okay, it is a unit vector. So, cos square plus sin square is equal to 1. Now, the equation of the line, the red line, let us call it, let us give it a name, this is B and this is A. Equation of line AB is what? It is n hat dot r or x, does not matter, dot r bar is equal to some constant, and that constant we are going to call T1, okay, some constant T1. And what is T1 measuring? It is basically measuring the perpendicular distance from the origin to the particular ray AB, okay, that is what T1 is. So, this distance this is at a point P1 at point T1. If you take the next one, the equation of this line B prime A prime is n hat dot r bar is equal to some T2, okay. and remember there is an n here. So, the theta is implicit inside here, right. So, your actual equation is x cos theta plus y sin theta equal to T1 and x cos theta plus y sin theta equal to T2, right. So, this is the equation of the lines, the line integral measuring. So, the detector picks up something that looks like this. We are going to call this function p theta of t. Okay. For a given theta, theta has already parameterized the normal vector or the perpendicular direction for the wave, for the light rays or the X rays, and t is the distance along this axis, right. This is t, this is our t axis. Perpendicular to the t axis of course is the direction of propagation, we will call that the s axis. Okay, so, we have an x y coordinates and we also have a t s coordinates. Okay. For a given theta you have two axes perpendicular to each other that are basically a rotated version of the x y coordinates. Okay. So, let us keep that in mind. So, p theta of t basically measures the f of x comma y along the line, whichever line at a particular t, which is parameterized now by ds. So, ds is along the line direction like this, t is telling you which line you are picking, right, and the integral is over s. Okay. So, in other words this is basically can be written down like this. I will explain what this notation means in case you have not seen it before. Okay. It can be written as a double integral with this function called a delta function or a Dirac delta function. Okay. The Dirac delta function has the following properties: it is infinite if x equals 0, it is 0 otherwise, and integral delta of x dx from minus infinity to plus infinity is equal to 1. Okay. So, just a way of sampling one particular value out of infinite of them, right. So, if you do for example integral f of x delta of x dx from minus infinity to plus infinity, everywhere else except at x equal to 0 delta is 0. So, this integral will basically vanish except at x equal to 0 where the integral is bounded. So, you will get f of 0. Okay. That is an important property of the delta function. It is basically a manipulative tool, it is not really a function in the conventional sense of the word, it is a manipulative tool that you can use to represent integrals in some form, right. So, when we wrote this double integral, it basically means that when you had f of x y delta of x cos theta minus t dx dy, it is only picking out, this delta guy is only picking out the values of f along this line, right, just like x equal to 0 was picked out here. This is picking out this whole argument equal to 0, and the whole argument is equal to 0 is the equation of the line, right. So, it is going to pick out the value of f along that line and you will get an integral in the direction of that line. Okay. That is a representation of the same integral. But nonetheless we will just assume that we have this fellow going. Where the integral is taken along s and x comma y are transformed to t comma s and they are taken along the line direction. Okay. So, this is our, this is what we will call a projection. Okay. This particular integral does not have t, it does not have s in it because s is integrated out, but it is a function of t, right, because depending on which line you take you will get different value of the projection. And just like if you look at the earlier schematic, the value here at T1 is different from the value here at T2 and so on, right. And so the P is obviously a function of t, it is also a function of theta, because if you rotate this in a different direction and then you do the same thing again, you will get a different functional dependence on t, right, naturally, because the shape is not symmetric. So this P theta of t is a function of two variables theta comma t, and it is exactly analogous to the original function. It contains the same amount of information as the original function, which is also a function of two variables x comma y, right. So if you had this P theta of t for all values of theta from 0 to 2 pi, let us say, we do not need all this, but let us for now assume that 0 to 2 pi is needed, and t let us say from minus infinity to plus infinity. This is equivalent, the information contained in P theta is the same as the information contained in f of x. Just like if you took a Fourier transform, the information contained in f of u v is the same as the information contained in f of x y, right. So this conversion from f to P theta P or whatever, this is called the Radon transform. Just like you had a Fourier transform, you have a Radon transform which is represented by this, okay. At some angle theta, some distance t, you find this line integral along a particular line, okay. So just like we have an inverse Fourier transform, there is also an inverse Radon transform. And that basically means that if you are given P theta of t, you invert it and get f of x y, and given P theta of t, by that I mean that you are given this functional form for all pairs of combinations of theta and t, right, just like you would need that for f of x y. Okay, so it is easy enough, let us just look at one example just to make sure that everything is clear for us. So let us say for example f of x y is equal to rho if x square by a square plus y square by b square is less than or equal to 1 and is 0 otherwise, okay. So this is our function, right, this is our cross section function, it is basically an ellipse, it looks like this or like this depending on which of a or b is larger. Inside this it is constant, right, and outside this is 0, okay. And you want to reconstruct this, and so the representation you will get if you pass light rays like this through this parallelly of course will be P theta of t, right. And so you can evaluate P theta of t using line integrals. I am not going to work this out because it is a little bit algebraic, but it is fairly straightforward to do. You basically take an ellipse like this, put the center of the origin of the center of coordinates, the center of the ellipse, sorry, and then you take an arbitrary line like this and then you parameterize this line and then you find for what values do you get extreme lines, right. So you basically have to get the coordinates of this point and the coordinates of this point, and for all values inside you will get a non-zero value of p, for everything outside you will get 0, right. And once you do that you parameterize by distance along this particular line, that will be your t, and this angle or the perpendicular pi by 2 plus this angle if you take the normal, that will be theta, and so you will get p of theta comma t, okay. If you do that, it turns out you will get an expression that looks like this. It is probably easier to work this out for a circle where a and b are equal, and the expression will become much simpler as well, but nonetheless. So you will get, if you do this transform, you will get something that looks like this. for p of theta t, okay, and a of theta of course is a square cos square theta plus b square sin square theta. Okay. So, the reason I put this example out is because this representation of what is inside here is intuitive, right, f of x y is rho inside a 0 otherwise, that is our actual object. So, its representation in this form is intuitive, but is absolutely equivalent to a representation of this form, right. So, if somebody came and gave you this expression and said okay, this is the actual object, it is giving you, it is just as good as giving you the first piece of information, okay. Just like if somebody told you the entire Fourier transform, you know the actual value by inverting. So, the Radon transform is identical, okay. So, the question now finally that we get to after this sort of background setting is how do we invert the Radon transform. Okay, how do you invert the Radon transform? Now, to do this there is something called the Fourier slice theorem, and this is what we will work out now. So, let us say we have our function f and I take a Fourier transform of it, f of u v, of course this is given by, remember we had this extra factor of 2 pi, so I am going to include that here. Okay, so this factor of 2 pi is now here and the small f is just obtained by inverting this transform, right. You have a plus sign here and you integrate over u and v as opposed to x and y. Okay. Now, if you take a single projection, so a given value of theta, so you fix theta first, so now it is a function of one variable along the line direction t, and you take a 1D Fourier transform of this. Okay, with respect to the t variable, because that is the only thing remaining, right. So, you take a 1D Fourier transform of the Radon transform along a certain theta direction. Okay. What do you get? We get something that we will call s theta of w. So, this is minus infinity to plus infinity p theta of t exponential minus 2 pi I t w dt, right, just like the usual 1D Fourier transform that we discussed. Now, the t dependence is gone and you get a w dependence. So, w is like your frequency, right, in the frequency domain. Okay. Now, this Fourier slice theorem basically relates this 1D Fourier transform to this. Okay. So, the Fourier transform of the actual Radon transform along a certain direction is directly related to the 2D Fourier transform of the actual function, right. Remember, our aim is to recover f, that is what we want to find out, that is the unknown. So, this is how you relate the 1D Fourier transform of the projection p theta of t at a given value of theta to a 2D Fourier transform of the function we are trying to determine. Okay. So, that is basically what the Fourier slice theorem tells us. Now, how this is related is what we will work out now. To do that, let us take the simpler case of theta equal to 0. Okay. Now, if theta equal to 0 degrees, then basically this is your object, this is your let us say x axis, this is your y axis, you are basically measuring along this, because remember the normal direction was what we used to set the value of theta, right, the normal vector. So, now all the actual light rays or x rays are going parallel to the y axis, this is x, this is y, and t is basically nothing but x. right, your t coordinate is horizontal because theta equal to 0 degrees. Good. So, let us look at the theta equal to 0 degree case. Okay. What happens here is, of course, t is the same as x coordinate, and so p theta equal to 0. Remember, we said this was for a fixed value of theta, right. You are taking a Fourier transform, 1D Fourier transform for a fixed value of theta. So, we will transform this. So, you will get s theta equal to 0 of w is integral minus infinity to plus infinity p theta equal to 0 of t exponential of minus 2 pi I w t dt. Okay. So, now t is the same as x, right. So, we will just write this as minus infinity to plus infinity p theta equal to 0 of x exponential minus 2 pi I w x dx. Okay. Now, what does the 2D Fourier transform look like of the original function, right. P theta is a projection, we are now looking at f. So, f of u v for theta equal to 0 is, let us take a look at f of u v comma 0 u comma 0. Okay. What does this look like? So, it is minus infinity plus infinity f of x comma y double integral, because you are integrating over x and y, exponential minus 2 pi I u x, because v is 0 dx dy. Okay. There is no v here because v is equal to 0. So, we are looking at the frequency vector u bar is basically u comma 0, right, just to see if we can relate the two of these two integrals. Okay. Remember, since t was the same as x, and if you look back at that figure we drew over here on the right bottom, s is in the ray direction and t is in the director direction, right. So, s is basically y, t is x, so s is basically y, correct. So, what is p theta of p theta equal to 0 of x is what? It is integral along y, because s is along y, of f of x y. Correct, because s is along the y direction. So, now we can put this and this together, and you will immediately see that this whole thing becomes quite obvious. So, f of u comma 0 is, we are going to split this integral. So, we will do this part first. Okay. So, we will keep the x integral out. Okay. This is p of theta equal to 0 of x because of this. So, f of u comma 0 is minus infinity to plus infinity. Let me erase this line, since you know what it is because of, p theta equal to 0 of x exponential minus 2 pi I u x dx. Okay. But this is nothing but the Fourier transform of p, 1D Fourier transform of p, right, which is nothing but s. That is what 1 is, right. 1 is the same, this guy is the same as this fellow. So, f of u comma 0 is nothing but the 1D Fourier transform at theta equal to 0, this s that we have here, but with w being replaced by u. So, if you take a single projection for a fixed value of theta and you take its Fourier transform, somehow it is related to the full 2D Fourier transform of the original function. Okay. Now, this is for a specific case theta equal to 0, but the idea is that okay, that is related, we have to get the exact relationship, and that is what we will do next. Okay. But I hope this special case situation is clear. Okay. Now, we will look at the more general case for theta not equal to 0. Okay. So, in general you have this pair of coordinates x and y, and you have this pair of coordinates, this is your s direction, this is your t direction, and you have some theta between s and t. So, you can in general convert the T s coordinates using a rotation matrix in terms of the x y coordinates. Okay. Now, to establish the Fourier-Treize theorem, we will work it out, it is just simple algebra, but you have to remember this fact, right, that the fact that you have an orthonormal coordinate system t comma s, which is only a rotated version of the original x y coordinate system. So, your t is basically x cos theta plus y sin theta, and s is minus x sin theta plus y cos theta, right. This is just a coordinate change under rotation, right. Remember, this was the equation of a line, that is where we started from. So, it is exactly the same equation, we are only looking at it from a different point of view. Now, we are looking at it as a coordinate change, one of the coordinates in the new pair of coordinates that we are using, the T s system, in terms of the original coordinates as a function of the rotation angle theta. Okay. So, if you do this, then the Jacobian of this transformation, which is basically the determinant of this matrix, will be 1, because you will have cos square plus sin square, and that is 1. Okay. And so, the area element dx dy will be the same as the area element ds dt. Okay. So, what we will do next is we will see how we can establish this for a more general case for theta not equal to 0. We will do the algebra, it will take a little bit of rewriting, and you will see immediately that this Fourier transform becomes absolutely critical in determining what the projections Fourier transform looks like, right. So, you can use the 2D Fourier transform to invert the Radon transform, and the Fourier-Treize theorem basically relates that, and we will work that out in the next session in more detail. Okay. So, in the meanwhile, please remember that this is not something new, right. We are just looking at the same thing from a slightly different point of view. We are treating the t and the line direction as new coordinates, and theta is something that parameterizes the new coordinates, right, in this. So, there are 3 things going on. There is this x y coordinates that you have by default, there is the theta comma t, which gives us the Radon transform, right, p theta of t, but there is also s comma t, which are new coordinates. So, in the Radon transform or in the line in the projection, you do not have s because it is integrated over, right, you integrate f over s. But now we are going to sort of work with all 3 of them, this being the Radon transform and this being used for this transformation here to relate the Radon transform to the original Fourier transform of the 2D function. Okay. So, we will work out some of these details in the next session.